Okay, so I'm getting some strange background noise coming through that speaker there, like water running. I don't know. You hear it? All right, we'll get going anyway while Eduardo tries to figure that out. Okay, so this is the third in the sequence. Sorry. I was picking up the air conditioning, is it? Okay. All right, amplified air conditioning, what we all need. So, third lecture, talking about the manifest fibre facility. So I started out giving you the general reasons why sharp imaging and wide fields are important. I then talked about GMTIFS, which is the epitome of the sharp imaging paradigm. Now I'm going to talk about manifest and why manifest capability to do very wide field is going to be very important for GMT, and indeed why manifest is arguably at least the instrument that is going to make GMT unique in the long term. Ah, that was good, whatever was done just then. Oh no, it's come back. All right, so here's the outline of the lecture. In accord with what I said in my first lecture, I'm going to try and give you a picture of how this idea has actually evolved. Manifest is in fact nowhere near as well developed as GMTIFS. GMTIFS is now towards the end of its preliminary design phase. It's a fairly well thought out concept in almost every area. We may not have designed every single nut and bolt, but we know how the instrument's going to work. We know what all the parameters are. Manifest is not like that at all. You will see as I go through this talk that some of the numbers change from time to time, and that's because none of the numbers have actually been nailed down. It's still fluid, it's still something we're developing. And in fact, one point I will make a couple of times is that we had an original concept which went with an original version of GMACS and an original concept for the Gregorian instrument rotator, and all of that's changed completely, and now we're going to have to redo our concept. So manifest is still at a very early stage and much more fluid than GMTIFS, so don't think of it at the same stage of development, think of it as being a much earlier phase. What I am going to do though is show you how we've got to where we are right now. I'll actually take you back and show you some of the slides for when I first developed the concept for manifest and when I first presented it. And you can see from that what things have stayed the same and what things have changed. So I'll start with that origins and the timeline. I'll then talk about TAIPAN, which is effectively a prototype for some of the key elements of manifest and an interesting instrument in its own right. Then I'll talk about manifest and the science and its modes. Manifest is a very versatile instrument. It's almost the antithesis of DAN's, no moving parts, nothing changes, any color so long as it's black, GMT nears. Manifest is anything goes, you can plug anything in anywhere. If you want, there's 1,000 fibers with, 4 IFUs with 63 fibers each. Sure, we can do that for you as well. My main difficulty in designing manifest is trying to contain that versatility and actually limit it to some number of modes that I can actually cram into my head. All right, then we will talk about the instrument design and go through some of the features of that instrument design. And then I will diverge at the end and talk about something else, which is actually getting wide field multi-object spectroscopy onto GMT at first light. At the moment, manifest is actually an instrument that comes right at the end of the development cycle for the first generation instruments. It comes after all the mirrors are in place, after the adaptive optics, finally you get the wide field corrector, and then you get manifest. And I'd like to argue that wide field MOS is so important and so valuable that in fact we should try and do it early, and I'll try and explain some ways in which we might be able to do that without costing GMT a lot of extra money. All right, so here we are talking about manifest, the fibre facility system, and remember that manifest is feeding both GMACS, the visible wide field multi-object spectrograph, and Andy's GCLEF, the high resolution shell. Again, just a reminder of a lot of the acronyms I'll be using here. MOS is multi-object spectroscopy. just means many objects at a time over a wide field of view. Imaging MOS, like GMACS, you actually take an image of the field and then you're putting slits over the images to constrain the field of view that's actually fed to the spectrograph, and then you're letting the spectra fall where they may on the detector. In Fibre MOS, you can collect the targets over a field that you're not imaging all of. The telescope has to image it. It's got to be somewhere in the telescope focal plane, but your instrument hasn't got to image anything except the fibre slit. And that means that you can take objects from a very wide field of view, bring them all down onto the fibre slit, and then very efficiently pack your detector with those targets. The other thing that MANIFEST does is integral field spectroscopy. It can look at individual objects and take a spectrum at many different points over the image of the object. So it's a different sort of imaging spectroscopy. You're not truly forming an image, you're just sampling an image with fibres and then feeding those to your spectrograph. But that gives you spatially resolved spectroscopy, and that's very important for many applications. And it's also important because it's a way of doing image slicing as well. As I've mentioned a couple of times, it's important sometimes you don't actually want the resolved image, but you do want to capture all of the light from your object, and you do want to increase the resolution of your spectrograph. And you can do both of those things by image slicing, taking the image, splitting it up into a small number of, or feeding it down a small number of fibres, and then putting those narrow fibres into a slit, giving you a very narrow slit so you get higher spectral resolution while capturing all the light from the object, because you're not actually putting a slit on the object, you're capturing all the light that goes down the fibres. And then of course you can combine the two and have multi-object integral field spectrographs, and in fact that is exactly what it sounds like, but that has the extra complication that you probably need multi-object adaptive optics as well if you want to do that usefully over much of the field. All right, so again, very versatile instrument, very capable of doing a wide range of science. I've already discussed the science that can be done with MANIFEST. I'll cover a couple of additional things in this talk, so it's not completely devoid of interesting science, but mostly I'll be talking about the technology and the instrument in this talk. Okay, so MANIFEST had its origins 10 years ago. Very nearly 10 years ago, November of 2008. Australia had just joined the GMT project in 2006, and we were beginning to think about getting serious about responding to the opportunity that had come up to build instruments for GMT. And I had long had this idea that I was sick of building fibre spectrographs where I actually had to build the spectrograph. And I thought the fun bit of this is actually building the fibres, not the spectrograph. I'll let someone else do that, and I'll just build the fibres. So what I wanted to come up with was exactly what its name implies. It's meant to be a many-instrument fibre system for GMT, okay? It's not meant to be an instrument in its own right, it's a facility. It has the same relationship to the focal plane that AO has to the point spread function. It's a way of manipulating and adjusting and changing the focal plane into ways that are useful to you in the same way that AO manipulates the point spread function. This was what I called the manifesto for MANIFEST at the time. And these arguments still hold. GMT is the smallest of the ELTs. It's got a 22-metre effective aperture in terms of collecting area, 25 metres in terms of resolving power, compared to TMT, which is 30 metres, and the EELT, which you'll notice has shrunk a bit since 2008. It was 42 metres at that time, now 39. But for sigma, or really d to the fourth science, GMT loses by a factor of between 2.5 and 10 to the other ELTs. So that's not a game that we necessarily want to play. Now, I'm exaggerating there, and we heard very nice arguments from Rebecca yesterday as to why that factor's not nearly as big as I thought. Nonetheless, it's certainly true. It's not an area where GMT can play to win comprehensively. On the other hand, GMT does have the widest field of view. In fact, it's bigger than I thought, because neither of the other two telescopes have used the fields of view that I thought they might be able to access back in 2008. The gain is in fact larger than I thought back then. GMACS doesn't offer this field of view anymore. It's now less than 50% of the full field of view of GMT, And of course, NEARMOS is not being built in the first generation, but will certainly not have a bigger field than that. WIFMOS on TMT has also shrunk. So for omega science, GMT wins, and indeed wins bigger than I thought it would, if it uses that full 20 arc-minute field of view. So this is the real punchline. GMT should exploit its strength as the wide field ELT by ensuring that every instrument that can benefit is able to access the full field of view and maximizes its potential multiplex gain. That's where I think GMT is going to find its long-term niche when all of these instruments, all of these telescopes are up and running. And that's what MANIFEST was meant to do. Oops. Oh dear. Okay. So I then wanted to find some particular principles that the instrument should try and follow. And the first one was do no harm. I wanted to be able to build this instrument without interfering with the things that Sheck or Darren DePoy want to do for GMACS, and I don't want to interfere with the things that Andy wants to do for GClef. I want to be adding functionality without causing them significant harm. So the system should not prevent any instrument working in whatever its native mode may be. It should be an add-on for every instrument. It should add value. Wherever appropriate, it should allow the instruments to access a full field of view and, if possible, provide additional functionality over and above field of view. So, for example, that might be IFUs, it might be image slicing and higher resolution, it could be various things. That paradigm required these three qualities, that the system was switchable, that you can move it in and out of operation, that it's modular, that you can add new instruments by doing a relatively simple modular upgrade to MANIFEST, and, well, that it's upgradable as well. This analogy is that the system is to field of view as the AO system is to the point spread function. So I then came up with an image for how this might work. And this is where, so most of those arguments are strategic. And strategy is really just common sense writ large, right? You can tell something's strategy if it doesn't really change because it's so fundamentally obvious and true that it persists over long periods of time. And those arguments all persist, although the details of the arguments have changed. The strategy has not. How the system might work, this is worth looking at just for the fun of how things actually evolve. I was actually imagining that it wasn't at the Gregorian station below the table, but actually was being redirected and sitting on the folded plane mount area, that the full field of view focal plane mounted on the instrument platform, you put Starbugs on that focal plane, 4 optics on each Starbug, including ADC and F ratio conversion, and then the fibers run from the Starbugs through conduits to the instruments. And you've got different sets of Starbugs for different instruments, that bit's still true, with different types of fibers and fiber slip mounts, also true. And all the Starbugs reside on the focal plane and could be used simultaneously. And a manual exchange of fiber slip mounts. I think we'll get rid of the manual bit. So I was imagining, even at the outset, that although I had a different concept for how the Starbugs would work, you'll notice these Starbugs have got little legs and walk around. I was imagining even at the outset that we'd have both single fiber type Starbugs and Starbugs carrying integral field units. That was intrinsic to the idea from the outset. Here's what I was imagining. Here's my focal plane, and I was imagining different sets of Starbugs. So these ones were going to feed NEARMOS, these ones GMACS, these ones QSpec, which I guess was a previous name for what's now GClef. It was certainly meant to be a high-resolution thing. I've forgotten about QSpec. And so you've got these fiber cables running off to GMACS and NEARMOS down in the Gregorian instrument rotator, and to QSpec, which I was imagining was sitting up here on this mount position. So that was the original plan. The version that we're looking at now is almost nothing like that. However, it did actually meet all of those requirements. One thing I'll note is that at the time I was imagining some interesting added functionality. For NEARMOS, with a fiber feed rather than a direct imaging spectrograph type feed, you could use OH suppression fibers. Now, I'm not going to talk much about those because we don't have NEARMOS right now, but we are still working on fibers which can suppress the OH lines in the near infrared. These are aperiodic fibre Bragg gratings that are actually printed inside the fibre and act as a filter, a multi-line filter, taking out hundreds, thousands of individual lines because you've got a very thick multi-mode grating in the fibre that you can put in. We're actually testing a system called Praxis on the AAT in the next year, and that will actually demonstrate just how well we can do with OH suppression in fibres. And if it turns out to work, it can suppress the near-infrared background from the OH emission lines very, very substantially and make a huge difference to near-infrared spectroscopy. For GMACS, I was imagining using mini IFUs. For QSPEC, which was the high-resolution thing, I was imagining doing image slicing. And I was also keeping in mind the opportunity of having Starbugs that were adapted for ground layer adaptive optics in order to really get the full vantage of GLAO. So this was then my sort of sales pitch slide. The strategic advantages of the manifest concept include enhancing the science case for several instruments. Well, I hope I've convinced you that manifest is able to do some really interesting science, both for GMACS and for GCLEF, and down the track we hope for NIRMOS or some such instrument. It adds powerful new functionality. We don't have OH suppression yet, but we will have the hexabundles, the IFUs. It doesn't directly compete with any existing concept, so I didn't want to get in there and say, look, this is a better way of doing things than GMACS. I wanted to be adding rather than having to add and subtract. Local advantages are that this was something that Australia's good at. It's something that Australia could actually contribute to GMT. And fundamentally, it's playing to GMT's strength as a wide field ELT. With manifest, GMT always will have an advantage that the other ELTs simply cannot have. And the other final thing is that it's relatively cheap. Compared to the other instruments, it comes at about half the price of almost all the other instruments. And it adds a lot of functionality, so it's very good value for money. Okay, so that was the basic idea, and that was in 2008. We did a feasibility study, which was just a 6-month study of this, which was done in 2011. We then went to an R&D phase, looking at developing some of the technologies required, and that was completed in late 2012. And we then went to a prototyping design study, which basically is the TAIPAN Starbug system. So I'll talk about this in detail, but basically GMT, not unreasonably, wanted to be convinced that this strange technology we had for positioning fibres was actually going to work, and it would work in a real telescope environment. Now, as it happened, I had my own plans for doing a big survey with the UK Schmidt telescope, and the two things came together very nicely, and so the prototype for manifest is also a working instrument for the TAIPAN sky survey. So that was a 3-year study, commenced in 2013, and the system was up and running in the lab by 2016, but the other elements of it, the refurbishing of the Schmidt and the spectrograph and other things, mean that the system won't actually be running on Sky until about May this year. The next step, though, for manifest is an 18-month pre-concept study that's just commencing. And so, you know, as I said, we're now at the pre-concept study stage. Further stages are the conceptual design and preliminary design, right? So we're at least 3 stages behind GMTIFS. We're starting a pre-concept, GMTIFS is finishing preliminary design. But nonetheless, our aim is to have manifests available so that it could go on the GMT in 2024, so shortly after GMT's notional first light. All right, so here's TAIPAN, our prototype. As I said, it's a fibre spectroscopy facility for the UK Schmidt telescope. The positioner is manifest prototype. It's got 150 Starbugs, which are the little self-propelling positioning systems that I'll show you more about in a moment. An assembly associated with that. Metrology for measuring where the Starbugs are in the field to make sure we can position them accurately. Acquisition and guiding systems, and all of that's actually coming together right now. There's also a spectrograph and fibre cable, a refurbishment of the Schmidt telescope. We got rid of all the lovely 1960s dials and flashing lights and installed a modern control system and modern drives for the telescope. And we're now doing full system testing. So right now, as we speak, Starbugs are running around on the focal plane in the Schmidt doing the initial system commissioning. That commissioning will be complete in May, and then we'll start doing science verifications, and by the middle of this year, I hope to have the TAIPAN survey up and running. Let me just tell you a little bit about that, since it's quite an interesting bit of science in its own right. The TAIPAN Galaxy Survey is aiming to look at 2 million galaxies over the southern sky. It's going to cover 2 pi steradians, 20,000 square degrees. It's going to exclude a 10-degree strip around the galaxy, a plus minus 10-degree strip around the galaxy, but it's going to go up to delta of plus 10. So it's 2 pi on the sky. The science is a combination of cosmology and galaxy evolution, and it'll be a reference survey for local galaxies. There'll be a complete sample down to IF17 of 1.2 million galaxies, and then another 800,000 galaxies going a magnitude fainter, luminous red galaxies, to increase the volume for the cosmology survey. That's what we'll be doing with the system in dark time, but in bright time there's going to be a stellar survey called Funnel Web. You'll notice that we're going with the poisonous animal theme here. TAIPAN is a large black snake that's very poisonous that you can find in Australia, and a funnel web is a equally large but somewhat hairier spider, which is also very poisonous and can be found in Australia. Not quite sure why we went with that theme, but there you have it.
It's also manifest, a very dangerous animal.
No, manifest is a completely harmless concept. You'll see this is our TAIPAN logo with the snake wrapped around the Southern Cross. The funnel web survey will actually make use of the Starbugs in a very interesting way, because it's taking very short exposures of very bright stars. You'll see that it's looking at stars between V of 5 and 11, aiming to get 100 signal to noise, and that takes just a couple of minutes with this system. And so they're really driving the speed of the repositioning, because they're completely limited by the speed with which you can reconfigure from one set of stars to the next. So that's a very useful survey from the point of view of driving that aspect of the system. And their goal is to pre-select suitable stars for the TESS exoplanet mission, and also to collect an enormous sample of stars with good quality spectra for stellar physics. And of course the third purpose of this whole project was to develop the TAIPAN prototype for MANIFEST. So the instrument capabilities are that we're using the full 6-degree diameter field of view of the Schmidt, so considerably larger than the MANIFEST field of view. We're going to have 150 fibres in phase 1, but I've just recently got another grant which will allow me to double the number of fibres, so we'll actually have 300 fibres. We built the whole system with 300 in mind, so we can fit 300 on the spectrograph. The field reconfiguration, we're sure we're going to meet the requirement of 5 minutes to reconfigure the field and go from one field to the next, and I am pushing hard to knock it down to about 2 minutes. The spatial sampling of the fibres is 3.3 arc seconds, so you can basically think of them as Sloan diameter fibres. The resolution in the blue arms, just under 2,000, but in the red arms, significantly higher at about 2,700. And we simultaneously cover the whole range from 370 to 870 nanometers. So this is the TAIPAN survey goals. We're actually planning to do a bunch of cosmology things. The first thing we're going to do is we're going to measure H0 to better than 1% with BAOs in the local universe. And here the goal is to explore this claimed discrepancy between the H0s measured from the distance ladder, which come in at around 73 kilometers per second per megaparsec, and the values that we get from Planck, which says that H0 locally, predicted from redshift 1100 down to redshift 0, should be around 67. And in fact, from our previous local BAO survey, the 60F survey, we also got 67, but with about a 4.5% error. We're going to drive that error down to 1%, and so really sharpen up to see whether that discrepancy is real or not. At the same time, we'll be looking at tests of the growth of structure, which can distinguish between different theories of gravity. As well as testing the cosmological model, you actually have a handle on whether you've got GR or MOND or something else. And then on top of that, we'll be measuring peculiar velocities for about between 50 and 70,000 early type galaxies, and from that we can also do additional tests of gravity. And then there's a large number of galaxy evolution cases as well that you can do with high signal to noise spectra for a couple of million galaxies in the nearby universe. So all of that's grand, but it all hinges on making the Starbug concept work. So what is a Starbug? So a Starbug is a extremely boring thing to draw. It's a fibre here running down to a little cylinder sitting like this, which sits on a glass field plate. And the light from the telescope, in this case the Schmidt, so the light comes in at the top, hits the primary mirror in the Schmidt and comes up to the internal focus from below, passes through a glass field plate, and the Starbugs are sitting on this field plate. In fact, they're vacuum adhering to the field plate. Now, the nice thing about this compared to many fibre systems is that it is back-wired. The human eye is front-wired. The reason your vision is not as good as it should be is because all the nerves to the cones and rods in your retina run across the front of your eye. They get in the way of the actual image you're trying to see. Octopus eyes are back-wired. They've actually got sharper vision than we do because the nerves come in from behind the eye and contact with their equivalent of rods and cones from the rear. Starbugs do the same thing. Unlike 2DF and other positioners where they have the fibres actually running across the focal plane and getting in the way of other places that you would like to put fibres, here the fibres come in from the back and don't get in the way of anything. But the really fun part about the Starbugs is that there's no robot required to do the positioning. Each Starbug is able to move on its own. And the way it moves on its own is, imagine a man standing inside one of those old metal garbage cans with the bottom kicked out of it, okay? So you're standing inside a thing, and I'm now going to put the microphone down. I'm going to demonstrate how Starbugs work. Okay, so imagine, imagine I'm standing in a cylinder which I've got on the ground. I pick up the cylinder, I swing it forward a bit until it bangs into the back of my leg, and I put it down again. And then I push myself up and swing my legs forward and hop. And then I move the cylinder and hop, and move the cylinder and hop, and repeat. It's incredibly ugly looking. And it works really well. So in fact, that's what they do. We have two piezoelectric cylinders, one inside the other. Right? Here's one inside, one on the outside. Here, the inside one is contracted, swung forward, and put down. You shrink the top one, swing it up, clip it forward, swing it down, and drop it. Okay? So it's doing exactly what I was doing. It's a one-legged man inside a garbage can, hopping along all the time. And it's doing that many times a second. And in fact, these things can move at centimeters per second. Okay, so it's incredibly rapid. You know, it's nearly as fast as an exoplanet reflex motion, right? So, what was it, a racing tortoise or something? I forget what it was Andy used, but it's moving it at about that same speed. But the nice thing about these things are that this is all solid state, right? This is all piezoelectric. There are moving parts, but they're solid state moving parts, right? You're moving the bulk motion. You're not moving one thing against another. So these things are very tough. They're very hardy. They're very long, hard wearing, and they are also completely independently movable, right? You're not having to do things sequentially. You're doing everything in parallel. Okay, so this is how they actually look in reality. So here is a Starbug. Here are the two piezoelectric tubes, and the fibre is stuck up the middle there inside a little mount. And then all of that runs back up here to a big ugly electronic connector at the other end, which could do with a bit more development. But this end is very small and beautiful. Inside here, we actually have an optic fibre. We have electronics to run the piezos and the LEDs that we use for the metrology. And we also have a vacuum tube. So we're running light, electrons, and air through these tubes, right? So they're all singing, all dancing, because these things are actually adhering to the glass field plate under vacuum. That's what's keeping them on the glass field plate. And they're pushing off that vacuum as they move along, okay? The metrology fibres around the edge on this one, here we're looking down the barrel of a Starbug. Here you can see the two piezoelectric things, the fibre in the very middle with its cladding and mounting, three LEDs, which are used for metrology, and then the gap between is where the vacuum is doing the actual sucking to hold it onto the glass field plate. All of these services, each one of these plugs into a connector plate like this, and all the services, the vacuum, the electronics, and the optics, all then run out of that connector plate, right? And that's completely fixed. The fibers are just moving on the end of their tethers on the field plate below. All right, so let's see how that actually works in practice. Here are some Starbugs. You can see the LEDs lighting up so that the Starbugs can be identified by the metrology camera that's looking at them. And now they're starting to move. They can spin as well as translate. And they can position themselves with, in this version, better than 10 micron precision. Now, on the UKST telescope, the plate scale is basically 66 arc seconds per millimetre. So 10 micron precision is more than adequate for our 3 arc second fibres. On the GMT, where you've got 1 arc second per millimetre, 10 microns is massive, massive overkill for what's actually required, even under the best conditions. But you can see these things all move around, and they all move around independently of each other. So it's completely parallel. That's why we can do things so rapidly. All, in this case, this isn't a fully populated plane. This is when we were still populating, but this will ultimately be, this is about, I forget, 50 or 70 fibres out of the 150 that will ultimately be on there in the first phase. And you can see that they're quite large. On the UKST plate, which is relatively small, right, it's about 350 millimetres or so across, right, they're actually taking up a lot of room. Each one of these fibres is about each one of these Starbugs is about 8 millimetres across, so about 8 arc minutes across, and with a little bit of buffer required between them, we actually have 10 arc minutes is the closest we can get things. Now that's fine for TAIPAN because we actually have to visit each field on the sky a minimum of 10 and often up to 20 times. And we're doing that because we've got a great big field of view, so we can afford to do that. On GMT, we're hoping to actually both reduce the size of the Starbugs down to of order 5 millimetres, and that means 5 arc seconds. And so we'll be able to put things much, much closer together then. Sorry, what was it? Vacuum. We're sucking through the fibre. The gap between the two piezoelectric tubes has got a vacuum on it, and that's sucking them onto the glass. That keeps them there. Now, the instrument assembly here, which sits within the Schmidt telescope, so these are the vanes running to the Schmidt telescope. This is the instrument assembly here. Up here is all the electronics. The connector plate is in the middle. Electronics and various vacuum distribution things are here. And then the fibres run from the connector plate down to the glass field plate here, which of course is very strongly curved. The focal plane in the Schmidt, of course, is strongly curved, just as the GMT field plane is curved. So the fibres actually have a nifty device called the bug catcher. So what happens if you lose vacuum, right? All the fibres fall off, and you've got to find a way to put them back on. So what we do is we've got a little device that basically is just a strainer. All the fibres run through this device, and then you can run it down to the focal plane and up again in order to put all the fibres back on if they happen to fall off. Now, in fact, they don't fall off because we have a large plenum which keeps the vacuum going for quite a long time, and an uninterruptible power supply as well. So in fact, it very rarely happens, but we do have a built-in mechanical safety system which means the bugs are safely contained should everything electronic fail. The glass field plate is 5 millimetres thick, about 350 millimetres in diameter, and has a 3 metre radius of curvature. Okay, and so we have ordered one of these. We've also coated it, so it's anti-reflection coated and hardened on the side with the Starbugs, so that the Starbugs aren't digging up the actual optic coating on the field plate. The field plate's mounted with 3 linear actuators for tip, tilt and focus, so that we can keep the whole field plate actually in the focus of the telescope. And there's a connector plate which distributes the Starbug services and the bug catcher, which I've already mentioned. There's a vacuum manifold on the telescope, and then there's another off-telescope one as well. So these are various aspects of it. This is the strainer, so this is the bug catcher. The fibres actually run through each of these 300 holes here, and then this drives down to the glass field plate and back again to re-put the bugs onto the plate in case of a vacuum failure. There's also a metrology system. The way that we know that we can position the bugs to better than 10 micron accuracy is because we can stare at each bug and find where these 3 little LEDs are on each bug, which gives us the orientation and the position of each. We actually measure it to 5 micron precision in closed loop, and note that our fibres have a 50 micron core, so we're positioning things to of order a tenth of a fibre core. And we're doing that with a CCD, which is just being used to image it. We mapped out the field distortion so that we've got a very accurate mapping of the positions between the glass field plate itself and the sky. And then we have some fiducials for locating the whole system mounted around the edge of the field plate itself. And this system has been tested, is working right now. It does actually work. This is now a working system. The guide bundles, in order to acquire a field and to guide the telescope, we have these coherent guide bundles, each of which has got 7,000 cores and cover about 1.5 millimeters in diameter, so that's about 1.5 arc minutes at the Schmidt. And there's 9 of these which we can position. They're just mounted on Starbugs, so we can put them anywhere we like across the whole 6-degree field of view. And the back end of these coherent bundles is re-imaged onto a CCD, and that then allows us to do acquisition of the field, guiding, measure the on-sky reference plane. We've actually got a focal plane imager, if we like. Can do the field plate, tip, tilt, and focus measurement, and we can also do the seeing and image quality measurements as well. So these 9 things are put on stars somewhere around the field plate, and then they go to the CCD where you can see where the stars are. And here you can see, this is a guide bundle, and you can see the tiny dot in the middle is a little bit larger in this Starbug, and that's because this is a coherent bundle rather than a single 50 micron fibre. There's also a complicated set of electronics. You saw a little picture of that in the movie. I'm not going to go through that in great detail, but there's separate modules for the positioner, for the mechanisms on the spider, for the detector, for the spectrograph, the acquisition and guiding, calibration. All of this is into these single modules, and you can simply add more modules. If you want more Starbugs, there's one of these modules for every 80 Starbugs. And if you wanted more Starbugs and you could jam them into the field of view, you just build yourself another module, build yourself another 80 Starbugs, and away you go. It's very modular, and that's, of course, one of the highly desirable things about this design. Here it is actually mounted on the UKST telescope. You can see it within the well. You can see the spider. Here's the spectrograph, which is a very standard 2-arm blue and red spectrograph, fixed format, very simple, not complicated. And this is us actually opening it. A couple of weeks ago, we actually had the Minister for Science come to the UKST telescope, and we had a large green button for him to push, which said, "Deploy the Starbugs." I said it should say, "Release the Kraken," but they weren't really keen to do that. And we had a very nice little ceremony, and in fact, it's the first time I've ever actually opened an instrument that was actually working. When we opened the 2DF spectrograph, we actually had 2 concrete blocks mounted on the telescope, painted to look like spectrographs, because that's all we had at the time. So I am getting better as I get older. I'm hoping that when we open MANIFEST, it'll be actually on sky observing. So here we can see a solar spectrum, so we're actually getting light through the Starbugs and the fibres onto our spectrograph, and they're now doing all the various commissioning tasks required so that this whole system can be on sky and working by May. Okay, so that's TAIPAN. We've very nearly got a fully operational working prototype for the system that we will use for MANIFEST. So this is a very comprehensive prototype. It's not a subsystem prototype. It's an end-to-end prototype for MANIFEST. It completely validates the concept. But, of course, there are a few little changes having to be made to go from a 1.2 metre telescope to a 25 metre telescope. They're not exactly the same. So let's have a look at what some of those changes and challenges are going from TAIPAN to MANIFEST. One thing is that the Starbugs point the other way. In the UK Schmidt telescope, they're looking down on the focal plane, right? Because the Schmidt light comes in the top, hits the mirror at the bottom, and the focal plane's looking down on the primary mirror. In MANIFEST, you're looking up at the secondary mirror, and so you've got to work it the opposite way. So the gravity vector is opposed. So we need to figure out what that means. There's nothing fundamentally difficult about that, but some of the details about adhesion and motion against gravity are going to need to be figured out. Then there's the fact that the UK Schmidt is a very low telescope. It's at 1,000 metres, and GMT is a little bit higher. What is it, 2,600 metres at, I think it's 2,600 metres at Las Campanas. So we have to worry about the fact the atmospheric pressure is different, and we care about that because we're using vacuum, and we don't want things to fall off, so we need to suck a bit harder. The test setup for dealing with these things is now being built at AAO, so we're building one the other way up, and we're evacuating it slightly, partially, in order to mimic these effects. We also have to do off-axis metrology. With the Schmidt camera, we actually have our metrology camera mounted at the center of the primary mirror. So it's actually looking back up on axis at the focal plane. I don't think that GMT is going to be very happy if we do that, so we need to mount our metrology off to the side somewhat of the main axis of the telescope. So we need to do some adjustments for that as well, and actually explore where we can mount the camera without having something else in the way or being in the way of something else. All right, so let's think about manifest, science and modes. So these are the things that we're trying to do with manifest, right? We're trying to increase the field of view for all the instruments, offer multiple deployable IFUs in a variety of sizes, increase spectral resolution where it's desirable through image slicing, use efficient detector packing, feed narrow spectrograph field from fibres with a wide field of view, have simultaneous observations with multiple instruments, the same GCLEF GMACS thing I mentioned earlier, and feed spectrographs at gravity invariant locations far from the focal plane. And if we can get it to work, use OH skyline suppression for near-infrared spectrographs, because if you can do that, it completely changes the game for near-infrared spectroscopy. So, how do we actually turn that into some real things? So, first of all, if you're going to see the wide field of view, you need a wide field of view corrector. You need the optics of the telescope to actually deliver the full field of view. And that's going to be important for anything that has low to moderate source densities, and for science cases that just need to cover a large area. If you're doing mapping of some class of object in, I don't know, the Magellanic Cloud, you want to map the whole Magellanic Cloud. And that means you don't want to be mucking around just looking at many sources in one area, even if they're dense. You want to actually have a wide field of view just to cover area. Likewise, if you're doing cosmology, you've got to cover a representative volume of the universe, and that means area. Multiplex, because we can pack things efficiently on the detector, we always have the opportunity to either have a bigger spectral range or to put more objects onto the detector. So we need to make sure that we use that. With GMACS, that's at least a factor of 2. With GCLEF, it can be anywhere up to a factor of 40, depending on how you actually want to use the spectrograph. With image slicing on an oversampled, we've got image slicing and oversampled detector, so there's no detector noise penalty from higher spectral resolution. We can actually increase the spectral resolution of GMACS by a factor of between 2 and 3, or we can simply use it for greater wavelength coverage. And as I mentioned earlier, we could run GMACS and GCLEF simultaneously if they've got targets in the same field and if it makes sense to do so. I mean, a high-resolution spectrograph and a low-resolution spectrograph, it's not often that these are going to be sensible, but I think in the target switching mode that we were talking about earlier, it does make sense, where all you've got to do is move the telescope. In terms of efficiency, you do have a reduction in efficiency because you're going to lose light going through the fibres, but that is going to be compensated by the increased efficiency of the spectrograph. You can build a more efficient spectrograph because it's easier to build a fibre spectrograph than an imaging spectrograph. and because you can have small IFUs capturing all of the target's light. You're not throwing away light at the slit as you do with an imaging spectrograph. And of course, for many science cases, multiplex or field of view just makes it a winner, even if there's an overall reduction in efficiency. Another issue that's often raised is sky subtraction, but in fact this is a solved problem. We've already showed that for very long duration exposures, if you use PCA sky subtraction, you can achieve a precision that is very close to the Poisson limit, down to at least 0.3% of sky and perhaps even lower. Now this depends on the number of sky fibers, the nod and shuffle mode you're using on your detector, source brightness and things like that. But in truth, sky subtraction is something that we can do very, very well now with fibers. Okay, so with all of those capabilities, what are the gains and opportunities? So one has to ask oneself, first of all, what science can only be done or done significantly better with manifest? And there are some cases that I've already highlighted: first light, an epoch of reionization, any sort of redshift survey, dwarf galaxy dynamics, near-field cosmology. Again, we want big fields of view and so on. So there's lots of cases where that big field of view really allows you to do something you can't do otherwise. See, IGM tomography, another case in point. The wide field and multiplex advantages mean that it's also good for transients, again, redshift surveys, but also extended targets. Now, we can offer IFUs with any mix. You know, we've got a fixed number of fibers that we can actually image on the detector, right? That sets the total number of fibers we can have, basically, right? But given that, we can reformat those fibers on the sky in any multiple of number of starbugs and number of fibers per starbug, right? So we could have, let's say we've got 1,000 or 1,200 fibers, whatever it might be, then we can have that in, say, 250 small image slices, where each image slicer just has 7 fibers, and you're trying to maximize the number of individual objects you look at. So you're maximizing multiplex and minimizing the spatial information per IFU. Or you can have something intermediate, or you can go to the other extreme and have big relatively large IFUs and a smaller number of them. And that's entirely up to you. You can figure that out. You've got to figure it out in advance. We can't build you a system on the fly. But we can have all of these different systems available. We've got plenty of room for parking multiple varieties of these IFUs around the edge of the field plate. So we can have several of these systems available, and we then just have to plug the appropriate set of fibers into the fiber slit position for the target spectrograph. We also are working hard to make sure that we don't do anything in designing the system that would preclude future GMT instruments, and I'll talk about some of those later on. All right, so let's just pop back and think about some of the science. So here's the intergalactic medium tomography that we've talked about a bit before, using some background sources like Lyman break galaxies. Our goal is to reconstruct the 3D small-scale structure of the IGM at high redshifts by very densely sampling the Lyman alpha forest over large areas of sky, right? We want to do two things. We want to understand the circumgalactic medium and the intergalactic medium, and we want to do that on very fine scales. We don't want to just have to stack all of our galaxies. We'd like to actually understand it around individual galaxies. So we need very dense background sources, but we get that if we use Lyman break galaxies. We can see the Lyman alpha forest in faint, dense Lyman break galaxy samples at redshifts out to, say, 3.5 or so. But the big advantage here, and the reason that this is really important, is that with the extra resolution that we can get from image slicing, we can actually start getting sub-megaparsec sampling of the IGM along the line of sight. And of course, you know, GMT's big aperture means that we're getting much better signal to noise in a comparable time on the sky. So here, this diagram actually reads right to left. It's an Arabic diagram. So here's the dark matter over density from some model, and the little green dots are Lyman break galaxies identified from the halos. If you sample those and look at the line of sight Lyman alpha forest field that the simulation also shows you, then this is the true Lyman alpha forest field that you would actually see. this is what you can actually reconstruct from this set of galaxies of the actual Lyman alpha forest field. As you can see, you can do a spectacularly good job using the Lyman break galaxies in reconstructing the actual Lyman alpha absorption field in the high redshift universe. All right, so that's one case where there's a clear case where MANIFEST can do something that can't be done otherwise because of its field of view and its ability to increase the spectral resolution in a useful specific niche. Another thing that's valuable is doing stellar chemical abundances in local group galaxies, right? Here you want to use the chemical abundances to trace the formation history of the Milky Way or other nearby local group galaxies. You want to get a large number of stellar spectra at reasonably high signal to noise. You want to look at, say, 100 RGB stars in each of 20 local group galaxies. You can do that in about 30 nights. And you can do that with MANIFEST in a way that would not be possible if you had to do them one by one with GCLEF. Archaeology of the outer Milky Way via chemical tagging, a similar sort of case, but this would be an extension of the Galar survey we're currently doing at the AAT, where we're looking at 1 million galaxies at R of 28,000 to chemically distinguish each one, looking at about 20-something different elements in order to decide which stars were formed coevally in the same association by using the common stellar chemical abundance label that each of those stars has. Now, GMT could take that program and extend it not just for the inner disk and bulge, but even to the outer disk and even the inner halo because of its greater aperture. So there's some really clear cases where MANIFEST can do stuff that just cannot be done otherwise, and I'm sure there are many more as well. So here are the basic requirements. We want to have at least 500 Starbugs, so we've got the sort of flexibility we're talking about. We also need about 25 Starbugs for doing acquisition and guiding. The numbers of fibers and Starbugs, these are the sort of numbers we're looking at. We're looking at having sets of Starbugs with single fibers, sort of image slicer mode with 7, and then 2 different IFU styles, and then having a large fixed IFU in the center of the field. The throughput for a given exposure time, including FRD, we're sure we can do 15%. We'd like to aim for at least 30%. The wavelength coverage and resolution needs to match the instruments that you're feeding. We can offer image slicing. The field of view of the instrument will be 20 arc minutes if we've got the wide field corrector, otherwise something like 10 arc minutes. The field of view in terms of fibers on each IFU is 3 arc seconds for a single fiber, and then variable, whatever you like, basically, for the IFUs. Positioning accuracy, easily better than 0.3 arc seconds. Starbug reconfiguration time, down to 2. Starbug lifetime, 5 years. So, if you do that, if you've got those basic technical specs, then you can do these sorts of science applications that I showed you before for GMACS, NEARMOS, when it comes to exist, and GCLEF, and you can meet the requirements for these different science cases. Okay, so this was the way that we tried to map this visually when we were doing the original MANIFEST concept. This is our mode map for MANIFEST. On the left, we've got GMT. We've then got a block diagram. So here's the telescope feeding MANIFEST, feeding spectrographs, and then we're saying the different ways we map from the focal plane to the spectrograph via here's a single fiber, here's a large IFU, here's an intermediate multi-IFU system, and so on. And then the green ones go to GCLEF, the blue ones go to GMACS, and the red ones go to NEARMOS. And you can see the number of Starbugs and IFUs in configuration, and the number of fibers per Starbug or IFU. So GCLEF, for example, you either had 43 or 4 single fiber IFUs, and that's the field of view of each one, 0.7 arc seconds, and so on through the mapping. So this is a way of trying to capture all the different modes that MANIFEST can offer. And the point of this diagram is to show that there are many different modes mapping multiple spectrographs to a wide range of different science cases. Now, of course, these modes won't all exist at the beginning because NEARMOS won't exist at the beginning, and indeed as I'll show you in a moment, the modes themselves have changed over time. But this gives you an idea of how you can think about it in a useful way. Oops, I've gone backwards. Okay, so how are we actually going to implement this? So I'm going to run through this reasonably quickly because the details here are still fairly uncertain. So the manifest fibre facility will feed GMACS, GClef, but leave open the possibility of feeding things like NIRMOS, but also, as I'll talk about towards the end, repurpose spectrographs like Hermes, Hector and Virus, existing spectrographs on other telescopes that turn out with manifest to be incredibly powerful on GMT. So here's what we have with TAIPAN, and here's the equivalent numbers for manifest. So we're increasing the number of Starbugs, probably fairly substantially. Likewise, the number of fibres, much smaller field of view. Interestingly, though, the radius of curvature of the focal plane is actually fairly similar between the Schmidt and the GMT. But the field diameter is very different, and the plate scale is enormously different. Okay, so we're also trying to leave open the possibility of having multi-object adaptive optics, and we'll certainly do GLAO. Okay, so this system here is our original concept, which will need to change, but at least gives you an idea of how it's being done. Here is the field plate, the curved glass field plate. So that's looking up at the secondary there. Here is the internal connector frame for the fibres, and then the fibres run up from there, and the individual Starbugs are sitting on the back of this glass field plate. And then from this distribution box, as it were, things run off either here to GMACS, down to GClef, sitting at the gravity invariant mount, so that's a nice long 25-metre fibre run. Whereas for GMACS, it's a very short run, and at least in the original concept, with GMACS just coming out directly here in the instrument side. The baseline wide field corrector and ADC design does exist, and it very nicely corrects the full 20 arc-minute field of view, but it's also very expensive. And at the moment, the GMT baseline does not include the... Someone else is talking. So the GMT baseline does not include the wide field corrector at first light. It comes much later, as I was saying earlier. So at AAO, they've looked at alternative designs that could be much cheaper, which could be affordable early on, and that's possible, though it has some issues. So at the moment, it's not quite clear what's going to happen about the wide field corrector. We have to do some additional redesign of the Starbugs for GMT. We need to develop the various multi-fibre IFU Starbugs and their 4 optics, but we have developed fairly similar systems for other instruments. So this is not something we haven't done before. In the original concept, the manifest positioner system, this part of it here, was actually stowed under GMACS in a half-size instrument bay. So here was manifest, here's the Gregorian instrument rotator, these are the various bays, and the top half of this bay could be something else, and this was manifest sitting down in here. But changes to the Starbugs, to GMACS, and to the instrument bay configuration mean that we need to rework the storage and deployment concept for manifest. It will still be down in here, but we need to rework exactly how it's going to be fitted in there. And deployment will, I think, be fully automated. This needs to be something that can be done without human intervention. Okay. So the glass field plate is also quite challenging for manifest. For TAIPAN, it's only 330 millimeters diameter, 5 millimeters thick, and you can order one of those. You can just go out to a manufacturer and buy one of those. For manifest, the glass field plate's nominally 1.3 meters in diameter, still 5 millimeters thick, and that's hard to make. It's a big, curvy thing that's very thin and potentially fragile. So that's got a significant manufacturing risk and hence cost. So we're looking at increasing the thickness so it's more like a conventional large lens. That reduces the risk because it's now much less fragile, but you then have to think about its impact on the wide field corrector design. You'd like a thick last element for manifest, so the first surface can be powered, but you'd like a flat last surface. Okay, so we've also got some ideas about the interfaces for GMACS and for GClef. I'm not going to go into these in detail because they're going to need to change because of the changes to GMACS. But basically the idea is that the front-end optics would have microlens arrays which feed the fibre bundle, and there'd be different configurations. And this is, of course, reliant on the original GMACS slit length and design. The pupil of the telescope's fed into the fibre and re-imaged onto the spectrograph grating rather than the slit. That's the current idea, with some overfilling. And there'd also be slides and slit masks to provide different alternative configurations, but all of that's still to be determined. Yeah, I think we'll leave that one. For GClef, well, we're working with Andy on the interface there, but the interface control documents have been drafted. There are designs for doing that, and I won't get into the details of that because it's not of interest to most people, but that is coming along quite nicely. The metrology, originally we were going to have 4 different CCDs up at M2 with a single commercial off-the-shelf lens. Now we're more likely looking at a CCD with a custom lens assembly, which would be probably mounted maybe at M2, but more likely on a spider somewhere. And that would allow us to more flexibly place where our metrology camera could be. So, Manifest is very much a work in progress. Everything about our original design needs to change, but I would emphasize that we have proved the fundamental technology. We are sure that this will work now. We just need to figure out all the details to make it work properly on GMT. There's a couple of other things that we're going to explore which aren't on our initial path, but which we will look at. One is MOAO mode, which would allow us to correct the field over each IFU individually. And we're looking at a miniature wavefront sensor, which is under development now, which would sit in the Starbug to serve as the sensor for the MOAO system. And then we need to look at a miniature deformable mirror, which would be the correction component of the MOAO system. But that's also being looked at. And then finally, there's the idea of doing spectropolarimetry, where you have a pair of Starbugs and a spectropolarimetry system feeding the different polarizations into each of the different Starbugs. This is something that we just have a concept for, but is worth thinking about for the future. All right, so in my last few minutes, I'd like to talk about putting a wide-field multi-object spectrograph at GMT at first light. Now, we've already got a first light multi-object spectrograph, GMACS, and that's going to do great science. Long-term, however, we really need to exploit the full field of GMT to have that unique advantage over the other ELTs. That wide field corrector is in there, but it's not going to be available at first light. It's planned for phase 3. So initially, GMT's got no full field multi-object spectrograph. So how could we go about providing that, a wide or full field multi-object and IFU spectroscopy for GMT at or very near first light at essentially no additional cost to GMTO? That's the critical thing. The reason this is coming later is because of cost. So wide field MOS requirements. 3 things you need are a wide field corrector, a fibre positioner, and 1 or more spectrographs. And there are various low-cost options for implementing each of these. So let me just quickly go through that. How could you do each of these things at low cost? So what about the wide field corrector? So we already have a full solution, but what could we do quick and cheap near first light? Well, the first option is to do nothing, to simply live with a 10 arc-minute field of view. That's already as big or bigger than anything that's available on any of the other ELTs, and significantly bigger than the GMACS native field of view. So the native GMT field of view is sitting there from first light. For MOS, you still need to do something about telecentricity corrections, but if we're going to have a powered field plate for Manifest, you could actually make that the corrector itself. So there's a relatively straightforward way that we could implement at least a 10 arc-minute field of view at almost no cost to GMT. Another option that's being developed by some of our US collaborators is an interesting concept called AWACS, which basically has local corrections with about a 2/3 fill factor over the 20 arc-minute field of view. So you get 2/3 of your 20 arc-minute field of view being corrected, and it might cost only $1 million as compared to the $10 million cost of the full solution. Well, we've got two positioner options as well. One is to bring forward MANIFEST. If Australia could simply find independent funding to build MANIFEST and make it an in-kind contribution to GMT rather than a cost to GMT, that's one way of doing it. It's not actually saving any money, but it is saving GMT that money. There's another alternative positioner that our Korean friends are looking at. I must admit, I'm not convinced about that. They're pushing that as a possibility, but I believe there's actually got greater design risk and probably greater total cost. So I think simply raising the money and doing MANIFEST right from the outset is the way to go. It gets interesting when you look at spectrograph options. We're going to have GCLEF and GMACS at first light, we hope. But if GMACS was not built at first light due to, say, funding constraints, it'd be nice to have some alternative there, right? So absent further funding, the lowest cost options involve repurposing existing multi-object spectrographs that are already out there. Now, the thing that makes this work is that the scaling between a 4-meter class telescope on a poor seeing site and GMT on a very good seeing site, when you've got the flexibility afforded by fibre image slicing, means that you can actually take some existing spectrographs designed for crummy 4-meter telescopes. I'm not looking at you, the AAT, but I am, looking at the AAT. It emerges that we can actually take existing spectrographs built for the AAT and put them on the GMT and feed them with MANIFEST, and they work just fine. So one option would be the Hermes spectrograph on the AAT. This is actually a reasonably high resolution, RF 28,000 spectrograph, which covers 4 bands with 400 fibres. So it's a high resolution, high multiplex spectrograph. It's what's doing that Galar survey of 1 million chemical abundances at the moment. It's an existing spectrograph. It's in operation right now. Another option, seems to have the same number for some reason, is Virus 2, which is funded to be built for McDonald 2.7 metre, should be on Sky in 2020, could be available for GMT in 2024. It's a low resolution RF 2000 optical spectrograph with 1,600 fibres, currently fed by a large IFU or deployable IFUs. A third option is called Hector. We actually have a multi-IFU spectrograph on the AAT right now called SAMI, but Hector is its big brother. It's being upgraded. So we're now seeking funding for that. In fact, we've already funded one of the 4 spectrographs we aim to build, so it's partially funded already. We should have it fully built by 2021, and again, it could be available for GMT in 2024. It's an RF 5000 spectrograph covering the full optical range with 4,000 fibres, and it's fed by deployable IFUs or a single large IFU. So we have all of these options potentially available. We'll have GCLEF, but we'll also have potentially Hermes, another high-resolution spectrograph. We'll have GMACS, but we could have Hector and or Virus 2. And that gives us a much wider range of possibilities. Now, we don't necessarily want all of these things, but we have fallback options, and we have some capabilities with these instruments that come for free, or at least purely as an in-kind contribution, which we don't otherwise have with existing instruments. And with those instruments, we then get the mapping between science modes and instruments that looks like this. We've got both GCLEF and Hermes doing this sort of galactic archaeology and stellar chemistry work. We've got Hector, which is very well suited for doing spatially resolved galaxies. And then GMACS, Hector, and Virus can all do the extragalactic science cases. So we've got an interesting set of possibilities for the future there. Now, if we want to see where these systems actually sit, here is an interesting way of measuring the power of a multi-object spectrograph system. Here's the total grasp, A omega. We've talked about this metric before. And here's the spectral power, which is the number of resolution elements and times the resolving power. And things along a line here are sort of comparably powerful. For a given detector size, basically things will lie along one of these lines here. So there's a 2K by 2K detector, 4K, 8K, and so on. These systems actually lie out here. You can see GMACS lies here on this diagram. TMT's MOBI lies there. GMACS with MANIFEST lies further out. Hector also lies further out. Virus 2 lies in around GMACS. So in fact, GMACS and Hector actually, with MANIFEST, provide the most power in this diagram. So that's an interesting thing that needs to be explored over the next few years and well worth thinking about. But I'll leave you with this summary and let you think about the science that you could do with one of these systems. Thank you very much.
Questions? So let me first. So in the beginning, I was thinking that to make an IFU, you would take several Starbugs and put them together. No, it's not the case.
No, it's not very efficient because the Starbugs have a significant buffer around them. How's that? Oh yeah, now it's got. So the Starbugs have a buffer around, so you can't pack them tight against each other. If you want a proper fill factor, you've got to put multiple fibers together inside one Starbug, which is perfectly straightforward to do. I mean, you can still bump Starbugs together. If you want a sparse array, you can do that, but it's not what most people want.
So those big ones, like for dark matter, you have that many fibers in a single Starbug?
The biggest ones, those very large ones, that's the fixed IFU at the center of the field of view. So that's because that's all the fibers you can fit on Hector or GMACS or whatever. So that's just all the fibers in a single IFU, which then goes to, so it's a single fixed IFU. But the other ones, the 19, the 91, those are deployable IFUs sitting inside a Starbug. Yes.
Okay. And then you can have some of those plus some fibers in the
Yes,
field?
you can have any mix you like. That's allowed. You've got to figure it out in advance, right? And you can't, it's not infinitely flexible, but we can offer as many modes as you're prepared to pay for Starbugs, or GMT is prepared to pay for Starbugs.
All right. So I have one last question myself. So you said that with GClef you can have up to 40 multiplexing capacity. So how can you fit all those?
You've got to limit your spectral range, of course.
Okay.
So you've got to pick a short spectral range. But if you only care about one feature or a narrow range, then you can do 40 at a time. So again, it's how you use your detector area. You can either cover all of it with one, big long shell spectrum, or you can pick a feature you care about and then pack that in for as many as 40 objects at a time.
Thank you. More questions?
So, talking about the IFUs, what's the maximum expected size for the deployable ones, on-site size?
I don't know an answer to that, but I'm sure it's bigger than the sort of 90 element ones that we're actually talking about now. So I don't know what the maximum size is, but I'm sure we can do a 90 element IFU in a Starbug.
Okay, so I'm supposing each one around 0.7.
Yep. Well, again, you could choose that, but yes, that would be an obvious number to pick. But you might choose 0.3, for example, and fully sample your field. But that's entirely up to you. So long as you can find a fiber of the right size or re-image onto an appropriate fiber, no problem. Each one will have a little focal plane, focal plane micro lens array is what I'm trying to say. Sorry, micro lens array sitting in front of it.
Among all the instruments we spoke about this week, this is the only one who doesn't start with G. How did you get away with it?
Yes, I don't know actually. It's
more seriously,
GMTIFS. No, it doesn't really work, does it?
can you say again? I was taking notes hectically and I missed it. the time scale of the TAIPAN survey.
Ah, yeah, so I don't know if I even wrote that down. So we're starting in the middle of this year. We're meant to run for 4.5 years from the middle of this year.
And last but not least, if people don't kill me because I keep asking questions.
No, that's good.
So when you commented the various options for various spectrographs,
Yep.
at the end, you mentioned, believe that, yes, the Hector is the replacement for SAMI.
Correct.
And you also mentioned that Virus 2 and Hector are still supposed to go on Sky. So
Are still...
supposed to go on Sky. They're still being built.
Yeah,
right?
so Virus 2 is fully funded, and will happen. Hector, we're still looking... We've partially funded it. We've built one of the 4 spectrographs for it, and we're looking for funding for the rest of it. But
so I guess my question is, why isn't SAMI an option? In others,
because SAMI isn't a spectrograph. It actually feeds the AA omega spectrograph on the AAT, and while they're prepared to lend us one of their spectrographs, they can't lend us all of their spectrographs. So I guess we could steal it if we really wanted to, but it wasn't an option I considered.
thank you.
More questions?
Sorry, me again. No, I think you mentioned earlier that the previous lecture that individual Starbugs could move for long exposure times
Yes.
to compensate. So how but for that probably you need the metrology lights.
Yep.
So
you do it between exposures, right?
okay.
Yep. So you're doing multiple integrations, right? And between each one, while you're reading it out, you do the metrology, shift things, and repeat.
Okay.
So it's not strictly continuous. It's discrete, but you can do a very long exposure with that and move it in between.
So, okay. Yeah. Keeping the
You could do
telescope
it.
tracking.
You can, of course, do it open loop continuously if you wish. That is a possibility. If you want to do it closed loop, you've got need the metrology, but you can do it open loop. Just drive them where you expect them to go.
Okay. Perfect.
Anybody else? If not, let's thank Matthew again.